Lesson 8.7 looks at graphing radical functions and inequalities and also transforming radical functions. I'd like to start by having you look at the warm-up, the first one where you identify the domain and range for each function, and the second where you are writing a translated function for the parent function that they give you, f of x equals x squared. So if you'll pause this now and complete the warm-up. Okay, looking at the first warm-up, f of x equals x squared plus 2, we can see that the domain is the set of all real numbers. Any value can go in for x. The range is going to be all y such that y is greater than or equal to 2, since we have the x squared and then the plus 2. Looking at b, f of x equals 3 times x cubed, the domain will be the set of all real numbers and the range will be the set of all real numbers. Looking at the second warm-up where we are writing a function g that is a transformation of the parent function f of x equals x squared. To translate that 3 units up, we have g of x equals x squared plus 2. And to translate it 2 units to the left, we have g of x equals quantity x plus 2 squared. Now, looking at the next section, you see that the graphs of quadratic parent functions and cubic parent functions, as well as the inverse, is in red. And with the first graph, the parabola, the f of x equals x squared, we can see that the inverse is not a function because it would not pass the vertical line test. So in order to have, certainly if we wanted the inverse to be a function, we would have to limit the domain of our f of x equals x squared to x being greater than or equal to 0, because then the inverse would be a function. And when we look at the cubic parent function and its inverse, we can see that both the function and inverse are functions. So, we don't have to limit that in any way. Now looking at the next section, a radical function is just a function whose rule is a radical expression. So we'll be looking initially at square roots functions and cubic root functions. I'd like you to look at 1a and 1b and pause this tape and plot a few points, make a table of values, and do enough so that you can get an idea of the shape of that curve. And I'd like you to do that for a and b. So make a table of values and then plot the points. When we look at 1a, we want to certainly in our table be plotting points that make our radicand, the value that we have underneath that radical sign, we want that to be positive or non-negative. So it could be 0 or anything greater than 0. So, I start by having my first x value be 3, which makes my f of x equal to 0. And that's going to be the smallest x value that I use. And, we can see that I plotted just a few points to get an idea of what that curve is going to look like, the square root, with the parent function being the square root of x. And here, because we've got x minus 3 under the radical sign, the domain is going to be all x's such that x is greater than or equal to 3, and all y's for the range such that y is greater than or equal to 0. Okay, so I'd like you then to move on to b. So when we look at b, f of x equals the cube root of x. To make things easy for plotting without a calculator, certainly I would use my x values as perfect cubes. And, so I have -8, -1, 0, 1, and 8. And when I plot that, I can see, the curve that I get. And I can see that the domain is going to be the set of all real numbers, and the range will also be the set of all real numbers. And with any of these, you want to certainly be checking them on your graphing calculator, even if we are, manually plotting them here. So I'd like you to move on, pause this, and try graphing C and D, and then start it again so that we can look at those. If we look at C, f of x equals square root of x plus 1, we can see that it really just shifts the parent function square root of x to the left by 1 unit. So, our domain is the set of x's such that x is greater than or equal to -1, and then our y's are the set of all y values such that y is greater than or equal to 0. And we can see what that curve looks like just by plotting those few points. Now if you'll move on, and we'll check D next. So if we look at D, where f of x equals 2 times the cube root of x minus 2, we know that we've got the x minus 2, which is going to shift 2 units to the right, and then we also have the stretch. So, we have some idea what it's going to look like just based on the transformations that we're used to doing. If we plot some points here, and, once again, I picked ones that would make the numbers work nice. So when we take a look at just a few of these points, we can get a good idea of what that curve looks like, and we can see that the domain is the set of all real numbers, and the range is also the set of all real numbers. We can see with the next few problems, and we're using exactly the same technique that we've used before. Now when we have g of x, it's the square root of x, which is our parent function, plus 5. That tells us that this is shifting f of x up by 5 units. So if this is our parent function f, then we just look at 1, 2, 3, 4, 5 units up, and we start from there, and we can pick a few key points, and then we can make our graph. So our function g of x is just shifting the f of x up by 5 units. When I look at this next one, b, we can see that g is f being vertically compressed by a factor of 1/2. So certainly 0, 0 would remain the same. We've got our f of x, our original function, and it's just being compressed by 1/2. So everything, we've got 0, 0, but then everything from that point on would be multiplied by 1/2. So it would look somewhat like that. Looking at number 3, we will be looking at f of x equaling the square root of x, and that will be our parent function, and then we're doing multiple transformations to that. When we look at a, we can see that we have under the square root sign x minus 4, which tells us that we are going to have a shift to the right by 4 units, and then we have the negative sign in front of the radical, which tells us that we are reflecting f of x across the x-axis. So certainly, we would, reflect f of x across the x-axis, and that would look something like this, but then we are also translating that 4 units to the right. So we'd be starting here instead, and then we would have the same shape. We're just shifting it 4 units to the right. So this would be our g of x, and we have our original f of x in red. Looking at b, g of x equals the square root of the opposite of x plus 3. We first take a look at that negative sign. It is taking the opposite of x only, which tells us that we're going to have a reflection across the x-axis. So that alone would give us a function that looks like that, from our original f of x. We then add 3, so that tells us that we shift that up by 3 units, and we end up with a function that looks like that, and that would be our g of x. When we look at c, we can see that 3 different things are happening to our parent function of square root of x. We have the 3 in front of the square root of x, which tells us that we are vertically stretching by a factor of 3. Because that's negative 3, we're going to reflect that across the x-axis, and then finally we have minus 1, which tells us we'll translate that down 1 unit. So our starting point will be here, and we've got that stretch, so by a factor of 3, so we can see that each point that we have with an intersection, instead of 2, it would be at 2, 4, 6 in the negative range. So we are looking at a function that looks something like that. In number 4a, we're taking the parent function f of x equals square root of x, and then we are reflecting it across the x-axis, which tells us that we will have a negative sign to reflect that, and it's also being compressed by a factor of 1/5. So we'll have a negative 1/5 times our square root of x, and we're translating that down by 5 units, so then we'll also have a minus 5. So that would be our g of x function. when we look at the next one, we're still working with that same parent function, f of x equals square root of x. But now, we want to be able to look at, what happens if we reflect it across the x-axis. So just as in part A, we know we're going to have a negative sign there. And we are going to stretch that vertically by a factor of 2. And then we are going to translate that up by 1 unit. So that's what g of x would look like.